In the next section, we look at one way of making sense of quantization. And the one reason you can give for quantization is that wave nature of matter, how particles can behave like wave, and how that can lead to quantization. So the waves corresponding to electrons in an atom, the orbital electrons in an atom, they must be able to fit on the circumference, kind of like standing waves on a string. So if you look at this diagram, if this is, say, an orbit of an electron around the nucleus of radius r, then the circumference of this orbit has to be an integer multiple of the wavelength associated with that electron. And if it's not an integer multiple of the wavelength, if 2 pi r is not equal to n lambda, then this orbit is not allowed, because there will be destructive interference when you go around the orbit with the wave associated with the electron. So only those orbits are allowed in which the circumference is an integer multiple of the wavelength associated with the electron. Kind of like how standing waves on a string, you can only have a whole number of loops in a standing wave pattern. You can't have 1.5 or 2.5 loop patterns. So it's a similar idea here. So that means if lambda n is the wavelength associated with the electron, the wave associated with the particle electron, then n times lambda n has to equal 2 pi rn, which is the circumference of the orbit. Now the wavelength, de Broglie wavelength, is h over p, or h over mv if we assume non-relativistic velocity. So using this expression for wavelength in this equation, we get nh over mv equals 2 pi rn, or mvr equals, which is mvr equals nh over 2 pi. And mvr is what the angular momentum of this electron orbiting the nucleus is. So we see how the angular momentum can only have values which are integer multiples of h over 2 pi. So this consideration, if you assume that particles or electrons in this case is behaving like a wave around the circumference of the orbit, then naturally we get the quantization of angular momentum. Now, quantization of angular momentum was an assumption made by Bohr, but based on these considerations here, assuming the wave nature of particles, this naturally comes out of that assumption. You don't have to assume that angular momentum is quantized. So you can say that it's the wave nature of matter that leads to quantization of energy levels. Only those states where matter interferes constructively are allowed, meaning if you have an integer multiple of wavelength equal to the circumference of the orbit. Let's look at another diagram here. So this is basically showing how an integer multiple of wavelengths are accommodated in different orbits. So this is the third and the fourth allowed circular orbits, and they have 3 and 4 wavelengths. So the first orbit will have one wavelength, second orbit will have two wavelengths, and so on. And that gives you the value of n. So n equals 3 orbit will have three wavelengths, n equals 4 orbit will have four wavelengths. And remember that n equals 1 corresponds to the lowest energy state. That's the smallest orbit or the ground state. Now, even though we're talking about these well-defined circular orbits of the electron, it turns out that electrons actually exist in a cloud of probability instead of well-defined orbits. In accordance with Heisenberg's uncertainty principle, when a probe is used to locate the electron in an atom, it ends up disturbing it. And so you make a large number of observations to figure out where the electrons are located. And from there, you get a probability distribution of electron location. So you cannot say what the precise location of the electron is. You can only point to the probability of finding the electron in a certain place. And it turns out that the Bohr orbits, the orbits of the radii predicted by the Bohr model, are the positions where you have the largest probability of finding electrons. But it doesn't mean that the electrons cannot exist at other radii. So this picture kind of shows you the probability cloud or the electron cloud around the nucleus. The darker portions of this cloud are where you have a larger probability of finding the electrons. So the first Bohr radius is the location, is the distance from the nucleus where you have the highest probability of finding the electrons. Now, we use a set of numbers known as quantum numbers to describe, to specify the state of an atom. And there are four quantum numbers. These are numbers associated with all of the quantized quantities, quantities that can only take certain discrete values and not continuous values. So let's start with the integer n, which we have already encountered. If you recall, the energy levels for hydrogen atom are given by the equation E sub n equals negative E naught over n squared, where E naught is the ground state energy, 13.6 electron volts. The integer n here is called the principal quantum number, and it indicates the size of the atom. Larger values of n indicate larger atoms. So in addition to the energy being quantized, we know the angular momentum is also quantized in general, and not just for hydrogen, but any atom. And so the quantization of angular momentum is represented by this equation. The angular momentum L is an integer multiple of h over 2 pi. And that integer is represented by square root of lowercase l times lowercase l plus 1, where lowercase l is also an integer which has specific values. Lowercase l can only have values that go from 0 to n minus 1. So first of all, l cannot be negative, and secondly, its smallest value is 0, and the largest value is 1 less than what n is. So for example, if n is equal to 2, if you have a hydrogen atom or any atom in n equals 2 state, then L can only be 0 or 1. If it's n equals 3 state, then for that state, L can be 0, 1, or 2, and so on. This lowercase l is the second quantum number called the angular momentum quantum number, angular momentum quantum number. So if n is equal to, well, if you're in the ground state, if n is 1, then the only value L can have is 0. So that's the angular momentum of electron in the ground state. Well, according to this equation, if you make L 0, if you make lowercase l 0, then angular momentum itself becomes 0. And that's a point of departure here. In the Bohr model, the smallest angular momentum you could have was h over 2 pi, but now that is shown to be actually 0. So you can have a 0 angular momentum as opposed to what the Bohr model predicted. And this is a reflection of one of the flaws in the Bohr model related to atomic electrons not being confined to well-defined orbits, but a probabilistic cloud. In the ground state, the electron spends time in and near the nucleus. So this is something which you wouldn't expect from classical physics or even the Bohr model. In the Bohr model, you have well-defined orbits of the electrons, but once you come to realize that it's actually a more probabilistic kind of picture, electrons live in a cloud and not fixed orbits, then it turns out that these electrons, first of all, are not just in those specific orbits, they can be in other places also, including inside the nucleus, And that's something really extraordinary. One would not expect these orbital electrons, as they're called, to be inside the nucleus. Now, having said that, I should also add that the probability of finding them inside the nucleus is extremely small, but it's not 0. So just like the first quantum number, the principal quantum number n indicated the size of the atom, L, the angular momentum quantum number, indicates the shape of the electron cloud. In multi-electron atoms, different L values for the same n differ in energy. So remember, the principal quantum number n is related to the energy of the atom. Now, for a given n, if you look at different possibilities of L, then each of these possible L values can differ in energy in multi-electron atoms. In hydrogen, they will all have the same energy, but in multi-electron atoms, even for the same n, different L's correspond to different energy levels. The third quantization has to do with the direction of the angular momentum or the spatial orientation of orbits. And this is mathematically modeled by considering the component of angular momentum in a specific direction, which is ordinarily taken to be the z-axis. The quantization of the z component of the angular momentum is given by this equation. Lz is equal to another integer m sub L times h over 2 pi. This integer ml can have values which range from negative L to positive L. So if L was 3, ML could have values -3, -2, -1, 0, 1, 2, or 3. This third quantum number, ML, is called the angular momentum projection quantum number. So what basically it indicates is the angle which the orbit makes. At what angle is it tilted? So if you look at this theta, you can have different theta values, and that would indicate a differently tilted orbit. Now, the direction of the angular momentum is found by a version of the right-hand rule where you curl your fingers like the electron is going. In this case, looking at it from the top, it's counterclockwise. And then your thumb is pointing in the direction of the angular momentum. So this arrow indicates the direction of the angular momentum here. And this angular momentum direction can be pointed in different directions, shown here. So it could either be this or this or this. Now, the quantization of this component of angular momentum, or this projection of angular momentum, means that the orbit can be tilted in such a way that either the angular momentum is pointing in this direction or this direction or this direction, but nothing in between. So that's yet another type of quantization. In a sense, you can think of it as space itself being quantized. So the orbit can be either like this or tilted a little more, but nothing in between. So the values of theta themselves are discrete values. For L equals 1, and that's what that picture shows. This corresponds to L equals 1. And then the values of ML can be -1, 0, or +1. Now, at the angle that the angular momentum makes with respect to the z-axis is given by this equation. Theta equals cosine inverse of Lz over L. So you can see that in this picture here. So this diagram shows an atom in L equals 1 state for which ML can be -1, 0, or +1. So if the angular momentum is pointed perfectly horizontal like this, that corresponds to ML equals 0. And then at this angle is where ML is +1, and this is ML equal to -1. And you see the angles theta 1, theta 2, and theta 3 are the angles between the z-axis and the direction of the angular momentum. So as I said before, theta can only have these specific values, these discrete values, and nothing in between them. And you can see from this right, if you imagine a right triangle here, say this one here, from there, you can see that theta would be cosine, or cosine of theta would be Lz over L. And that's how you get this equation here, that theta is cosine inverse of Lz over L. If the atom is placed in an external magnetic field, if there's a magnetic field present, then and only then different ML values correspond to different energy levels. If there is no magnetic field present, then all of the ML values correspond to the same energy for a given L. The third quantum number has to do with fundamental properties of particles. Electrons and other atomic and subatomic particles, fundamental particles, have a property called intrinsic spin. It's kind of like the electron or other particles are spinning around their own axis, kind of like how the Earth does. Now, that's just a metaphor used to describe this property. So it's not that the electrons or the particles are actually spinning, but they seem to have a property which suggests a spin. So in any case, this is called the intrinsic spin or spin. And this gives rise to another quantum number, which is the intrinsic spin angular momentum. And that is quantized in both magnitude and direction. So represent the intrinsic spin angular momentum is represented by capital S and is equal to square root of lowercase s times lowercase s plus 1 times h over 2 pi. So again, it's an integer multiple of h over 2 pi. As far as the spin quantum number s, lowercase s, that has a value of 1/2 for electrons. Other particles have other spins, but electron has a spin of 1/2. And then if you look at the z component of the spin, that can have like two different possibilities. These are known as spin up or spin down. So sz, the z component of the spin, is given by another integer ms times h over 2 pi, where ms is either negative 1/2 or positive 1/2. And you can think of this as the electron either spinning clockwise or counterclockwise, that the spin angular momentum is pointed upward or down. So sz is the z component of spin angular momentum. ms is the spin projection, it's called the spin projection quantum number, and that has values of either plus 1/2 or negative 1/2, spin up or spin down. That comes out of this equation. So now we have the four quantum numbers which together describe the state of a system like electrons in an atom completely. So it gives you a complete description of what's going on in an atom. So the state of a system is determined by these four quantum numbers, n, l, ml, and ms. Again, that's the principal quantum number n. N is the principal quantum number which indicates the size of the atom. The allowed values for n are 1, 2, 3 positive integers, basically. The second one, lowercase l, is the angular momentum quantum number, which can have values ranging from 0 to n minus 1. So for a given value of n, L can have these values. And L indicates the shape of the orbits, or the shape of the probability cloud of the electrons. Next is ML, the angular momentum projection quantum number, which tells you about the orientation of the orbits, what plane the orbits are in, and that ranges, the values of ML range from negative L to positive L. And then finally, we have the spin projection quantum number, which can have only two values, either negative 1/2 or positive 1/2, spin down or spin up. This diagram shows the shape for different quantum numbers, the shape of the orbits for different quantum numbers. So this is the simplest one here, where n is 1 and L and ML are both 0. So the state is 1, 0, 0. And that's the probability cloud. As you can see, it's spherically symmetric around the nucleus. And then when you get to n equals 2, now with n equals 2, there are the possibilities for L are 0 or 1. So this first one that you see here is n equals 2 and L equals 0 and ML equals 0. So that's what the probability cloud looks like for that state. For n equals 2, L equals 1, and ML equals plus or minus 1, notice how the shape of the probability cloud is kind of flattened relative to this. So earlier when I said L, the value of L indicates the shape of the electron cloud. This is an illustration of that, how these two shapes are different from each other. And then for n equals 2, L equals 1, ML equals 0, the shape is completely different relative to these two here. And then this gives you different possibilities for n equals 3. So as you can see, the picture becomes more and more complex as you go to larger n values. And again, the darker the coloring of the cloud, greater is the chance of finding the electron there. Clouds don't look like or correspond to classical orbits. Uncertainty principle actually prevents us and nature from knowing how the electron gets from one place to another. And so the idea of orbits, it really does not make a whole lot of sense, although we still use the language of orbits simply for convenience. But just keep in mind that there is no underlying reality to the existence of orbits. It's all about the probability cloud. Let's look at problem number 38. The problem is, what, if any, constraints does the value of ML equals 1 place on the other quantum numbers for an electron in an atom? So the key thing to keep in mind here is that if ML is equal to 1, if ML is equal to 1, that means L needs to be greater than 0. That all that comes from the constraints that L and ML have on the values of each other. So just to remind you, ML has to be anywhere between negative L to positive L. So using that relationship, if ML is 1, L has to be greater than 0, or L has to be greater than or equal to 1. Because the value of L cannot be less than ML. And then when you go to the relationship between N and L, if L is greater than or equal to 1, then N has to be greater than 1. Because L has to be less than N. The maximum value L can have is N minus 1. So this means N has to be greater than 1, or N has to be greater than or equal to 2, because L cannot be less than 1. And there are no constraints. This doesn't put any constraints on the value of MS. So the question had asked, this specific value of ML, what constraints does it put on other quantum numbers? So it demands that L has to be greater than or equal to 1, N has to be greater than or equal to 2, but it doesn't put any constraints on the values of MS. Let's look at problem number 42. How many angles can L make with the z-axis for an L equals 2 electron? If L is equal to 2, then ML can have one of these 5 values, -2, -1, 0, 1, or 2, which means there are 5 angles that are possible for this situation. So the answer to part A is 5. And then calculate the value of the smallest angle. So that's basically using the equation theta equals cosine inverse of LZ over L. And then you plug in the expressions for LZ and L that we've seen before. And you cancel out the h over 2 pi, leaving you with this. So theta is cosine inverse of ML over the square root of 6, because L is equal to 2, so L times L plus 1 is 6. Now we have to find the smallest angle. Smallest theta would correspond to largest ML. Remember the graph of cosine function looks like this. So as you go from 0 to pi over 2, the value of the cosine function decreases. And that's the reason why we say that the smallest theta corresponds to the largest ML. If the value becomes, if the angle is larger, the value of the cosine function is smaller. So there's an inverse relationship. In any case, theta minimum is cosine inverse of 2 over root 6. So that's the largest value, 2. And that comes out to 35.3 degrees. Okay, we'll finish this chapter in the next video.